Hello vintage computing folks. Today it's time again for another round of Microtronic programming.
Microtronic Program 2090 ready.
And we are continuing our series of, how to program these extremely limited educational computers from West Germany from the 1980s. So we already had a couple of videos in this series. Our running example is a program that adds the first n natural numbers, right? So for something like n equals 3, you would expect the program to return 6, because that's what 0 plus 1 plus 2 plus 3 is. And we already implemented an iterative version using a loop, 8-bit, on both the Microtronic as well as the CP1. And in my last video I showed you how to implement a recursive version of this summation program on the CP1. Today we are going to implement a recursive version on the Microtronic, and so it's already the third or fourth video within a week or so. You guys must think, well, this guy is nuts, whom is he making all these videos for? He's getting like 3 likes and 20 views, so why bother, right? And well, actually, I have to say I'm mostly making these videos for myself. To remind myself, right, of how things are done basically on certain platforms. And and the other reason is I'd like to learn to speak English more fluently, right, because natively I'm German, right, speaking, so speaking English fluently on the fly is somewhat of a challenge sometimes. So these videos actually help me to basically get talking, so to speak, right? So I hope you don't mind. All right, so on the CP1, of course, if you implement a recursive function, you need something like a stack, right? And on the CP1, we don't have stack instructions, basically. There's no stack built in the architecture, right, in this virtual instruction set, but the machine offered indirect addressing as well as indirect branching, and with that it was basically possible to emulate a stack, right? Implement a stack by hand, basically using the indirect addressing modes, the analog of C pointers, if you like, right? And we use this to set up 2 stacks, one for the local variables, for the values, right, of the recursive functions, and one for the return addresses, the return stack, right? So we will need 2 stacks, one value stack and one return stack. And on the Microtronic, I mean, it's a Harvard architecture, so you cannot write programmatically into the program memory, right? So the machine has an address range from 00 to FF, 256 12-bit opcodes here, right? But you cannot programmatically use this memory space for data, right? So it's only for programs. And unlike the CP1, where you, of course, have a shared program and data memory, right? 127 addresses without memory expansion, and it goes up to 255 with memory expansion. But on the Microtronic, you have the registers instead, right? So you have 16 4-bit registers from 0 to F, right, for your data, and then there's another set, a background set of registers, a background bank, so to speak, right, which adds another 16 registers. So, and you can basically exchange the upper bank, A to F, with a background register set, and the lower bank with the background register set, right? And so the idea is quite simple, of course. For recursive program definition, you want to write the program so that independent of the invariant of the invocation depth of the program, right, you'll always want to use the same registers, say C to F, right? And so for C, maybe we have the sum so far, C and D, right, and the counter in E and F, right? So all the program is expecting basically the current local variables of the current recursive invocation of the function in C to F, right? And then in order to now implement a stack, you can basically shift these registers down and up, right? So basically here I shifted the registers down, right? And now I have the upper 4 registers C to F available again, and I can write new values into it. So this is how we are going to implement push and pop the value stack, right? So we are using basically the extra bank, the background bank 0 to F, right? We are using the normal, the foreground bank for the for communication with the extra bank, right? And for basically passing in values and reading values out, right? And for example, the final result of the sum will be in 2 and 3, and all the current counter is in 0 and 1, and so on, right? And also the normal bank will be used to implement the return stack. So the value stack is kept in the background bank, right? But the return stack starts at register F, E, D, and goes down, and so on, right? Yeah, so for our program we need 8-bit variables, and we need 2 of those, one for the counter and one for the sum. And that of course means, so each stack frame needs 4 of those, right? So each shift is basically 4 registers down, and that means you won't have more than space for more than 4 value stack frames, right? So the maximum nesting depth for our program will be 4. And this is of course much less than we could do with the iterative version, right? Where we actually extended the version to above 8-bit, right? So in the end we had a 12-bit version and could go up to 992, which was the sum of n equals 44, if I remember correctly. But so here we are of course limited to 4, as just explained. So the maximum result will be 10 then, right? And but yeah, still, I mean, it's a fully general implementation of recursion on the Microtronic, and I'm going to go through the program with you. But first, let me load it. So I have my PicoRAM 2090 extension board here, right, which is an SD card interface for the Microtronic, as well as an SRAM emulator, right? So you see it's actually plugged in instead of the 2114 SRAM circuit here. And I can load a program basically from SD card, so I don't have to type everything in, right? And the program I'm looking for is called recursive sum. There it is. Loading now, and now we have it in memory. And let's start the program we just loaded, and start with the base case, which is, in this version it's 1. Okay, the sum of 1 to 1 equals 1. And for 2 we are getting the result 3. And you see it takes a long time for this poor little Microtronic to do its work, right? We have 6, and as I mentioned, the max is 4. By the way, PicoRAM also shows you the instructions that are executed. So let's execute this with 4. You see currently the machine is executing a kin keyboard input, wait for keyboard input, right, operation. This is because it asks for the value n now, and I'm putting in 0 and 4, right? And you can see that it shows the mnemonics as well as the program opcodes and the address, right? And so there is another kin, so, and it stopped, and you can see that it correctly computed 10. Okay, so this is just to assure you that the program is working. So let's get started. First, we are clearing the registers again. As you know already from our previous experiments, this is F08. Then we are basically doing the same stuff that we did for the iterative version, right? So we are displaying the D and E register on the display, and we are now inputting into registers E and D the 10 position and the 1 position of the input N, right? So then given that the Microtronic needs hexadecimal, right, we convert this into hexadecimal, right, with F04. And then we are clearing the display again, because the machine runs much faster. So we turn the display off. And now we have the hexadecimal result in DEF, right? And so we said that we are going to use 0 and 1 for the counter, right? So we got to copy the D register to 1 and the E register to sorry, the D register goes to 0 and the E register goes to 1, right? So, and now we have to make sure that we supply the N argument to the value stack, right? And for this, we first need to bank in basically the value stack, right? I said that we are going to use the background register set for the value stack, so it doesn't interfere with our normal registers, right? And the goal is to get the counter into E and F in the background bank, right? And this is why I also have this line here, because that separates basically the background register set from the normal foreground registers. And the opcode for doing this, for banking in the upper bank of the extra registers and swapping it with the current foreground upper register bank, is FOE. And of course now the lower registers, they stayed, right? So I still have the value that I just copied from the result of the decimal to hexadecimal conversion in 0 and 1, right? The counter low and counter high nibbles, right? So, and I can now basically use this to communicate with the background register set that I just swapped in, banked in, right? So I copy basically 0 to F now and 1 to E. Okay, and then we restore the normal register set by, swapping the banks again. So now the upper bank has been swapped back into normal state. And as I said, we are going to use a return stack, right? And given that we cannot jump indirectly, we have to emulate now returns to different addresses somehow. And one way of doing this is simply to use numeric values, right? And then basically have something like a branch block in the code which looks at these numeric values, right? And just does a conditional branching based on the value, and then does a go to the right address, right? So I'm setting aside a label 1 here basically, and I'm writing 1 into register F, which is now the first, the top of the return stack basically, right? And what 1 means basically is go to a certain address, which I'll show you in a second, right? So this is what the branch blocks then will have to do. So if 1 is in the on top of the return stack, then it means go to a certain address. So now we actually do we have prepared now the call basically to the sum function, right? We have read in N from the keypad, we have converted it into hexadecimal, and we have copied it into the right destination, the top of the value stack, and we have set up the return stack by putting a numeric 1 label there as a marker. And now at address 22, go to 22, we actually have the program start, right? The sum computation, and so that'll return, right? And the jump block will basically continue here, which is then displaying the result basically. But the result is in the background register set, right? So again, we need to swap in now the background upper bank right here, so that we can read out the computed value, right? And we arrange it in such a way that the sum is in registers D, C, and D, right? And so D is a lower value, the low nibble of the 8-bit result, right? And we copy this to register 2. And C is the high nibble of the result, right? And we copy this to register 3. And then we swap back the foreground register set, the upper bank, using FOE again, right? So now we can actually also basically do a subroutine call here, which is, restore, basically pop the value stack, right? And just to clean up basically, what we are going to do is basically bring this back into that state, right? So we are popping the value stack, and for this we basically have a subroutine, and B90 is where that subroutine lives, address 90, and B is go sub, and go sub return, right? So the Microtronic allows for one subroutine call, no nested subroutine calls, because it has a single return address register, right? And we are calling this 4 times because, as I just said, we need to shift 4 4-bit registers for one value stack frame of 2 8-bit variables, right? Counter and sum. And also we are popping the return stack. This is what B60 does. And now we can actually display the result. So we are moving now the result into the D register, because this is where, the result is an hexadecimal, but we need to convert it into decimal and then show on the display, right? And so we are moving the result to the DEF registers, and that's because DEF are the registers where the FO3, the convert hex to decimal instruction opcode, expects its arguments, right? And then we can just, display the result, display 3 registers DEF, right? So the result is now in decimal on the display, and we are simply waiting for keyboard input, right, in order to do a new round. So go to 0 0 means start the program over again. So we are now quite far, right? I mean, we have the base call of the program implemented, right? And input, compute, output. Now we need to implement the actual summation function, right, in a recursive way. So let's go to page 2 if I find it. There it is. So we are now at address 1C, and remember that I said that for whatever reason the summation program starts at address 22, so we have a couple of no ops there, and this is where that starts, right? So I mean, first we have to swap in the value stack now, right? FOE brings in the background register upper bank in the foreground, and now we are comparing if the counter is 1, right? So in this case we are terminating at 1 because I wanted to have one more stack frame available, as we only have 4, right? Otherwise we would have only been able to compute the sum up to 3. If so, then we don't branch, right, to the inductive case, but now we have the base case, right, at address 27 here. So we now simply have to make sure that we put the result on top of the value stack frame, right, into the registers that we allocated for this, which is C and D. So we are putting D into 1 into D, right, and we are putting 0 into C, and it's low high low high. Usually it's low high, right, but the stack grows down basically, so this is a better direction for this. So we loaded the result for the base case to simply return 1 for 1, right, and now we need to actually return from this recursive invocation, and for this we have we first have to swap back in the normal bank. Remember that we started basically the sum function by swapping in the background bank, right, A to F. So we are restoring the normal upper bank, right, with FOE again, and then we are going to this piece of code which I'm calling the jump block. And this jump block basically now looks at the top of the value stack. Let's actually have a look there, right? So as I said, the return stack is basically F, E, D, C, B, and so on, right? So it basically, and then we have these numeric labels now in the return stack. So the label 1 means if the top of the return stack contains the label 1, then we are going to address 0E, right? And 0E is actually after 0D, where we made the first call to our sum function at 22, right? So it would then continue there. So, and in the same way for the next label, for which we are using 2, right, we will continue at another address, which is coded here, address 39, right? Again, at address 38, we have the recursive, quote-unquote recursive call to the sum function, and then this will return by jumping to this jump block, which I just showed you, right? Which will then, depending on the label 1 or 2, for 2 it will continue at address 39, right, as I just showed you. If the label is 2, then it continues at address 39. And yeah, that is basically then executing the return from the base case, right? Else at 2b, we are starting with the inductive case, right? And so we gotta do a little bit more now. Again, we start by restoring the normal foreground register set. And now we are doing, because we now need to prepare a recursive call, now we are shifting down the value stack, right? And we are going from this state into this state. And for this, we again have a subroutine, and at B70, right? And again, we are shifting the stack 4 times, 4 registers down. And then now we are swapping in basically the foreground upper bank again. So given that we have shifted down the stack, right, and we are preparing a new stack frame, we now have to make sure that we are getting the right values in the stack frame that we just prepared for the recursive call. And for this, we are just copying now the values from the underlying stack frame, the one which we shifted down, right, into the counter value basically. So the counter is at FE, right, low high, and we shifted it down, right, to BA. So we are now making a copy. We are copying B to F, and we are copying A to E, right? So we now have a copy there, and so we want to make the recursive call, of course, for n-1, right? But we just copied n. So in order to get n-1 in F and E, we have to subtract 1 now from F, and then also prepare the underflow, right? And the underflow now does not go to the next higher register, but to the next lower register, which would be E, right? So carry underflow. So now we have n-1 in F and E, and we also have to work with the return stack now. So first of all, we are done with the value stack. We are bringing back the foreground upper bank, right, with FOE. And now we are shifting down the return stack by 1, right? So basically F goes to E. And we are putting a symbolic label now here. The same trick, right? So this is now the 2 label, right? And the jump block will then return at 39, and I already showed you that, right? So the jump block says, so okay, if the label is 2 on top of the return stack, then you continue at address 39, right? So this is where we put that return label 2 onto the return stack at address 37, and then the recursive call to sum now with n-1 argument, right, is at 22, and this is where the computation continues after the return, right? So at FOE, so what do we have to do now? Now we have the result of the n-1 sum in the CD registers, right? And now we have to basically add CD and the current n values together to get the result for this invocation level at n, right? So for this, we got to bring back the foreground upper bank again, right? And now our results are, you know, actually in C and D. This was the sub result from the n-1 call, right? Now we are copying these values back into the stack frame underneath, right? So we are copying D to 9 and C to 8. This means we have the n-1 sum now in 8 and 9, or 9 and 8, as I should say, low high, right? And now what we are going to do is, so we are done with the value stack, right? So we are bringing back the foreground registers again, because now we want to shift the stack up, right? So we're shifting the stack up 4 values, right? And now we have the sum that we just saved, basically, from 8, 9 is back in C and D, right? So, and we are bringing back the values, right? The background upper bank. And now we do the addition. And we do this by using the addition code F4, right? And we are adding the current counter, right, to the current sum, which is the sum n-1, because we copied it from the underlying stack frame before we popped it, right? So we are copying the counter to the value, making sure that the overflow carry is considered correctly into the C register, right? Because this is low-high. And yeah, now we will also pop the return stack by using B60, which is another subroutine, right? And again, we can then return from the recursive case, from the inductive case, right, by jumping to the jump block, which will consider the numeric labels and continue the computation as specified. Yeah, so that's basically the program, right? That's all there is to it. Now we only need to implement our helper routines. So at address 50, I said, okay, here we have a procedure that pushes up the return stack, right? And that's pretty simple. So basically you copy, you know, the register. So you want to have F and E, E and D, D and C, and so on. But if you do in this way, of course, you would overwrite the registers, right? So you have to do it from the bottom up, right? So you copy 9 to 8, then you copy A to 9, B to A, and so on, right? And you can tell that I only set aside basically 8 registers now for the return stack. So, I mean, the value stack doesn't make more than 4 anyway, right? So it would have sufficed to only do this for 4 entries on the return stack, but, you know, doesn't matter. So this is more general subroutine that can be used for other recursive programs that supports nesting depth up to 8 then in the for the return stack. And FO7 means return from subroutine, and as I said, there can be one call return, but no nested calls returns, right? Because FO7 only does not maintain a stack, but there's only a single return address. Okay, so that was that. And then we also have a procedure that subroutine that pushes the shifts the return stack up, right? So, and that's of course the other direction, right? So you copy E to F, D to E, C to, so all the values go up one level, right? Also just a couple of move, basically a few move instructions, and again it terminates with FO7. Now the game continues now for the value stack at 7T. So, but remember that we are using the background registers, right? So in order to swap in the upper bank, you already know FOE is used, right? This exchanges registers A to F. And we are using all of the 16 registers, right? So we also swap in the lower bank now, FOD. So now all the registers are background registers. And I simply do a brutal copy, basically. So, right. So 1 goes to 0, 2 goes to 1, 3 goes to 2, 4 goes to 3, and so on, right? Until we finally arrive at F goes to E, right? So we pushed all the registers down one level, and then we restore the normal memory banks, register banks, sorry, and then we return. And the same, then we also, now we shifted the stack down, the value stack down. Of course, we also need to shift the values stack up, and this is at address 90, right? So same game, but in the other direction, right? So again, we swap in the background register bank, and then E goes to F, D goes to E, C goes to D, and so on, right? Until finally 0 goes to 1, right? And then we restore the normal register set and return. Yeah, and then the only other thing is the jump block starting at B0, and I already showed you that, right? Because we don't have, one more time, because we don't have indirect branching. So, and yeah, you just put the right, jump target addresses in there, and for the different labels, numeric jump labels you created. And then F00 means halt the program. This is just a check basically if a jump label occurs, you know, maybe due to stack corruption that is not expected, then the program will terminate. Okay, so let's run this one more time. And ironically, of course, we didn't even need, you know, 8-bit registers, right? Because the stack doesn't allow more. Oops, 40 for sure doesn't work. But 4 works, right? And that's the max. So because all our values would have can be stored in 4 bits, but you know, so for 0.5 I'm simply getting a wrong result now because I don't have enough stack frames. Yeah, and it might not even, well, it terminates, but with a nonsense result. Alright guys, so that's it for now. And yeah, I'm planning 2 more videos. So one is actually Towers of Hanoi on the CP1, right, which is a little bit more interesting recursive program than the sum program here. And the same on the Microtronic, right? So, and actually I already have the version of Towers of Hanoi for the Microtronic, right? And of course this is a classic textbook example of a recursive definition, right? So I can show you that PicoRam already has a Hanoi program here. So, and I can also already run it, load it, and I'm going to show you in my next video